Okay, so we are live. Hi, everyone. Just a quick show of hand or thumbs up if you can hear us and see the screen. I think there's a bit of latency, so it's going to take a couple seconds. Welcome to the session, and sorry for the delay. We've been having some tech issues. This is the first time we are doing this setup, so understandably, there was a high chance of things going wrong as we were doing the setup. Can you comment on yes, if you can see us and see the stuff on the screen? The guys on YouTube and LinkedIn. Anyone?
So I can't see anyone on my side.
Can someone comment on the audience, please? Those of you on YouTube. Oh, I see blank screen. Someone is saying, yeah. So people are seeing, yeah. Perfect, yeah. I see you, a screen, white, blank. Yeah, perfect. That's it. So welcome everybody to this first ever AMA session. Yeah, I think we might regret to call it Ask Me Anything. Yeah, indeed, it's actually Ask Me Anything, but with some boundaries. You shouldn't ask us how to use category theory to go to the moon. We wouldn't be able to answer that. Yeah, that's a bad joke. So welcome everybody. Just a quick one before I get off the screen and hand over to our host, Adrian, to introduce himself and kickstart the session. Just a quick comment on the logistics. So I've had quite a few people asking me questions about, how to ask questions. So the easiest way is for you, as you are now, attending, you put your comments, your questions on the comment box. That's it. If you wanted to be on stage like us, with us right now, to ask your question, and then we can have some sort of discussion, then you would have to fill in the form on the website. Let me give you the website for those of you who are just joining now. This is how you do it, but I'm afraid it's too late to do it for this session, but in 2 weeks' time, you can do that. So just fill in this form. It should pop up there. And then we will reach out to you. And ideally, we would ask you to, send some sort of a question ahead of time so we know more or less, because what we want with these sessions to be on stage is to have some interesting, questions that lead to some sort of a discussion as opposed to just generic yes and no type of questions. So that's it from me. So if you wanted to be on stage with us next time, just fill up the form. So without a further ado, I'm going to disappear now and hand over to Adrian, but I will be around. And I will also, Adrian, I will be highlighting the questions. You will see them on the screen. Just give me a second. So so everyone enjoy this session, and I'll see you soon.
All right. Hi, everyone. My name is Adrian. I'm a mathematician. I specialize in geometry theory and category theory. I did my PhD with Andrew Blumberg at the University of Austin, Texas, and then I was a postdoc for a while at NYU, Abu Dhabi, with Hisham Sati and Ush Haiba. And now I'm working for Bombardier, who's my boss now. I'm working for Zaiku, where I'm applying simplicial methods to quantum measurements. And today I'm here to answer your questions. So the more questions you ask, the better, because then I can tailor what I'm about to talk about to your needs. If I don't get any questions, then basically I will just start defining categories and functions and things, and then just intersperse answers to the questions that you've sent me via email. All right, so do you have any questions you would like me to answer right now, or some questions you'd like to put in the comments so that I can see them? All right, so let me quickly pull up the questions from that Bumblebee had already sent to me. All right, so if I don't get any more questions right now, okay, so Michael writes that starting an overview would be great. So I'm speaking mostly off the cuff, and everything will be very informal, and just don't don't hesitate to just write with questions. You can also tell me to skip things if I'm being too basic, or you can tell me to go into more detail if you'd like me to. Also, a quick heads up: I'll be speaking for roughly 1 hour, so maybe until 8:30 UK time. Okay, let's see. So Michael says that he would like me to definitely get to adjoints and natural transformations. Great. So okay, so let me just quickly define what a category is and quickly tell you about why you might care about them, and then I'll try to get to adjoints and natural transformations as quickly as possible. So first, and I'll start off informally. So informally, all right, so to make the talk more interesting, I'm pretending to have really, really bad handwriting. And so let's see. So informally, whenever you have, when you have some sort of object of the same type, right? So for example, sets or vector spaces or groups or topological spaces, and some form of way of going from one such object to another. So way to go from X to Y, right? So X and Y, they're both any one of these guys. So whenever they're one of those, and there's a way to go from one to the other, then you probably have a category. These arrange into a category. All right, so now formally, as a definition, a category consists of some structure and some properties. So a category consists of let's give our category a name. A category C consists of a set, which we call, object C, which are the objects of C. And for all pairs inside of objective C cross objective C, we have a set, again, a set denoted C of X and Y. And these are the morphisms from X to Y. So this here is the name of the set. And now we have two more pieces of structure. We have for all triples inside of the objects of C. A map to denote like this, which goes with a map from the set, the product of the set of morphisms from X to Y and the set of morphisms from Y to Z. To X to Z, which we usually just denote by a little circle. And let me just switch the order of these two guys for a reason that is about to become clear. So in pictures, what's going on here is we have so the morphisms from X to Y are usually denoted by F over an arrow. So we have F from X to Y and G from Y to Z, and this gets sent to X to Z, F composed with G. So here you see G was an element in the morphisms from Y to Z, and F was an element in the morphisms from X to Y, and then their composition is denoted by this little circle here, as you can see down here. And then there's one last piece of structure, which is that for all objects, for all objects in C, there is a special morphism, idx, in morphisms from X to X, called the identity on X. Right, so this is a lot of structure. This is everything that goes into defining a category. And all of the structure, and now the structure has to satisfy some properties. And whenever we introduce properties, after we've introduced structure, we usually say such that. So we have all of the structure and we want it to satisfy the following properties. We want that A, whenever we have four objects, W, X, Y, Z, and a morphism between each of them, then we want this to satisfy associativity. So if I compose F with G and then compose this with H, this is the same thing as first composing G with H, and then composing this with F. Right, so there should be a for all here. And then also, whenever we have X to Y, let me do this a little differently. All right, so whenever we have a morphism X to Y, we have these identity morphisms, then we have that F is the same thing as FP composed with identity morphism, which is the same thing as F post composed with the identity morphism at Y. So whenever we're in this situation, we have a bunch of, whenever in the situation we have a bunch of, as I said, when you have a bunch of things of the same type, right, so a bunch of things of the same type and some way of going from every type to the other, then you probably have a category, which means you probably have one of these things here, and then you have to check all of these properties. So let's just check this. Let's just see what this means in the example of sets, for example. This is the most basic example. So in this most basic example, so we're now looking at sets. Then our set of objects are going to be, then our set of objects are going to be sets. Oops, that's not the color I wanted. Then our set of objects are going to be sets. Now, some of you might already have heard that the collection of all sets is not a set, and I'm just going to ignore that. You technically have to consider the set of all small sets. So, for example, you could consider the set of all finite sets, and then you'd be fine. And then for any two objects, you want a set of maps from, so for any two sets X and Y, you want a set of maps which and will denote our category of sets like this. So we want a set of maps from X to Y, and this is literally just going to be just maps of sets. Right, so for example, if X equals the real numbers and Y equals, I don't know, let's take X to be R squared and Y equals to be the real numbers, then a map, then we could have as a map from R squared to R could then be given by sending X comma Y to, I don't know, X squared plus Y cubed or something. Right, so, and so keep in mind that when you do mathematics built on axiomatic set theory, then maps between sets don't have to be defined by formulas the way I just defined them. It's just literally any consistent assignment of, for every element in X, some element in Y. Right, and now So let me speed through the rest of it. So now you have to check that for any three sets, x, y, and z, and any two maps, one going from x to y and one going from x to z, that you can compose them. And this composition will just be your typical, your standard composition of functions. So for example, if we have z also equals to r, and we have a map going from y to z given by sending, I don't know, t goes to log t or something, this map is called G, right? Then you get a map F composed with G, which takes X and Y to the composition of X and Y goes to X squared plus Y cubed, and T goes to log T. So we have to substitute in X squared plus Y squared into T, and we get log X squared plus Y cubed. Right, so, and then finally the identity function for any X is literally just given by id X goes from X to X, and you just send small x to small x. And then what you need to do is you need to verify all of these axioms. You have to check that if you now have three maps between sets, and you then compose them the way you usually would, and then you compose the first two the way you usually would, and then compose with the third one. That's the same thing as composing the second two the way you usually would, and then pre-composing with the first one. And then you also have to check that post-composing any map with the identity map just gives you back the map you started off with. And if you're completely new to this, I would very much encourage you to go on Wikipedia or something and look at all of these, take all of these examples and just very stupidly go through all of this structure and all of this and all of these properties. Just because from a pedagogical perspective, like once you've understood what a category is, all of this is very easy. But when you encounter this for the first time, this is a lot of information. So there's a lot of stuff that you need to digest, and you really just need to stupidly check that you have all the structure, and then check that you have all the axioms for several examples before it really sinks in. Okay, so I got a question for references. So, I mean, I'm right now not using any particular reference because, I mean, this is the stuff that I know, but I can tell you which two books I like the most. So, oh, actually, I'll recommend three books. So the first one is, let me just double check quickly that I get the titles right. Just one moment. So I'm just typing all of these names into Google. So let's see. So the first book is by Tom Leinster. So this is Leinster, Tom Leinster, Basic Category Theory. And this is, in my opinion, probably the easiest book to learn category theory with, or at least it was when it came out several years ago. I haven't been maybe newer books have come out in the meantime. So let me just write quickly. So this one here is very easy. Well, relatively easy at least. And also just exceptionally clear. A different book in a similar style is by Steve Awadey. Right, so, and his book is called, let me just check. Very surprisingly, it's called Category Theory. And so before I tell you a bit more about this book, right, so if you read so one book that I would definitely not recommend, so I won't write it on the I won't write it down, is the Category Theory book by Saunders MacLean. So even though Saunders MacLean is one of the people who invented category theory and was at the time one of the greatest experts, his book is not particularly pedagogical and also goes into nitty-gritty details on set theory, which at a first pass can easily be skipped, and only when you really start getting into the details of category theory do you need to start worrying about set theory. And Awadey, and in the preface to his book, Awadey references this book by Saunders MacLean. He says Saunders MacLean is made for the working mathematician, and his book aims to be the one for the rest of us. So Awadey's book is very much written with computer scientists in mind, and it's also relatively self-contained. So most books on category theory, because category theory aims to unite and compare disparate parts of mathematics, they'll also always have tons and tons of different examples coming from parts of math that you're maybe not familiar with. And Awadey very much tries to avoid doing this and only gives examples which he defines in the book. But it is very technical, and it is quite dry, in my opinion. And let me just finish by what's probably my favorite book, which is by Emily Reel, and this book is called Categories in Context. And this is, in some sense, the exact opposite of the previous two books. It's based very much on trying to explain as many examples as possible and tries to really explain as much as possible why you would care about categories in various mathematical contexts. But it also goes really, really deep into many subjects, and in many situations, I think that Emily chooses the correct explanation, which I'm always very happy with. But the correct explanation is not necessarily always the best one to start with. So let me just add that Awadey's book is maybe aimed more at computer scientists, and Categories in Context is really goes deep and has many examples. Right, and you could really, I think this trifecta makes a really good combination. So you could try to like if you're very ambitious, you could try to read real, and then whenever you get stuck, move to Leinster, and then when you've unstuck yourself, continue with real. But working through real will take a lot of time and energy, which you may or may not have. All right, let's see, any new questions? No. Okay, so so now we know what a category is. As I said, you should, even if it's painful and annoying, you should really, if you're seeing this for the first time, you should go and grab some examples from Wikipedia and just check, does it have all the structure? Does it have all the properties? So let me give one more example of, so let me give one more example of a category, and this will be the category of monoids. So let me quickly tell you what a monoid is. Sorry, it's getting quite warm in the room where I'm sitting. Let me open the window quickly. Okay, so George is asking, how do the references that I mentioned compare to Levere and Chanel's conceptual mathematics? Compare. So I've looked at that. So the last time I looked at that book was probably over 5 years ago or something. And the way I remember that book is that it's very much aimed at conveying the main concepts of categories to a non-mathematical audience, but that you may have a hard time learning to actually use categories from reading that book. But again, it could be good in combination with the books that I suggested, like, maybe if Leinster and Awady's book seem a bit dry, I think that Levere and Chanel's book could be good just to get a more conceptual explanation of what's going on. Okay, so Sebastian asks, so what's the point of, so if I understand Sebastian correctly, you're asking, what's the point of introducing the category of steps and functions when you can talk about the category, when you can talk about steps and functions without knowing about categories? And this is a valid question. So there are somehow you're welcome, George. So in my mind, there are sort of two levels of category theory. So we have two levels. Oh, this wasn't supposed to be CT. This year was supposed to be CS. So computer science. So we have two levels of category theory. So level one At this first level, categories serve more as an organizational principle. And here, what is, so here the salient feature is that categories are the structures that you encounter over and over again. So sets and functions are a category, topological spaces and continuous maps are a category, smooth manifolds and smooth maps are a category, groups and group homomorphisms are a category, vector spaces and linear maps are a category. And what you will discover is that you will be doing the same thing over and over again in many categories. So for example, in the category of sets, you can take the product between two sets, right? So we already we already encountered the product actually inside of we already encountered the product inside of the definition of a category. But in case you don't know what this means and you just zoned out at that point, right? So the product of two sets is when you just take pairs of elements from one set and the next. So for example, if you take the product of the set, one all the way until 8, and you take the A all the way until H, right, then this gives you a chessboard. Where some element in here is 5, I don't know, maybe this is E or something. So this is a thing that you can, but you'll also encounter a notion of product inside of vector spaces and inside of topological spaces. And what you'll discover is that in all of these categories, they can be characterized the same way. So there's a thing called the there's a categorical notion of a product, and there's also any notion in category theory admits a dual notion, and you get the dual notion by just putting the word co in front. So there's a notion of co-product in categories. And so then at this organizational principle stage, at least two things happen. Whenever you get a new category, you can say, well, in the categories that I already know, I was able to construct these things called products and co-products and kernels and co-kernels and push-outs and pullbacks and so on. And you start looking for these structures in these new categories, and you will discover interesting new constructions that maybe you wouldn't have thought of doing otherwise. Right, so I kind of think of categories at this level as being some sort of fancy IKEA furniture, where there's this like the perfect little box in your bookshelf or something for all the things that might come up in a category, and you know exactly where to put everything. And in a second, we'll also get to functors between categories. So a functor is a way of going from one category to another, and often these functors preserve structures. So for example, there is a functor going from pointer topological spaces to groups called the fundamental group functor. And this functor preserves these coproducts, which I just spoke about. And it also preserves products. And this is super useful for computing things. All right, so we've gotten a bunch of new questions. All right, so Sebastian now wants to know if we can derive anything new. And at this organizational principle stage, it's you can't really do anything that you wouldn't be able to do without categories and functors and natural transformations. But that being said, there are many things that you would be less inclined to think about without knowing about categories, functors, and natural transformations. Right, so this is basically what I was just saying. Like, it wouldn't necessarily occur to you to wonder what coproducts are in groups if you didn't know about category theory. I mean, so just to be clear, coproducts in groups are older than category theory, but if you approach it for the first time, I think you're more inclined to think of these interesting new constructions if you know about category theory. So LinkedIn user asks, universal question mark. So yes, all of these things that I've been talking about are universal constructions. All right, so Tony would like to know, right, so I don't actually know, despite the thing I'm working on right now having the word quantum in it, I don't actually know much about applications of category theory to quantum mechanics the way I suspect that Tony is hoping for. The only work that I know of which brings sort of conceptual insight into the foundations of quantum mechanics is work by Bob Kuke. And even there, this is very limited. This is really for quantum systems. It doesn't deal with any sort of dynamical situation. So first of all the Hilbert spaces in Kuke's and friends' work are finite dimensional, and there's no dynamics. So there's no solving Schrödinger equations or anything like that. All right, so getting back to the more big picture, yeah, so right, so Sebastian just noted that one can define topological quantum field theories as a certain functor. I think this was more in response to Tony's question, but let me just mention that I think this is actually fits in well with what I was saying before. Like, you can define at least sort of classical topological quantum field theories in the sense, or conformal quantum field theories in the sense of a tier. You can in principle define without knowing about categories and functors, but then, you know, instead of just saying Bordisms form a category and a quantum field theory, a topological quantum field theory is then a symmetric nodal functor out of this category into vector spaces, you'll then have to spell out every single time basically a lot of what I've wrote up here because you don't have the language to describe it. You'll have to say over. So one other thing that category helps you with is it's not saying the same thing over and over and over again. You don't have to say, oh, and now we have an assignment to every d-1 dimensional compact manifold some vector space, and to every borders in between two such manifolds a linear map, and so on. You can just say it's a functor, and then you're done, basically. So getting back quickly to my big picture explanation. So yeah, so in the first instance, category theory functions more as an organizational principle. As I said, I think of it more as like as a piece of IKEA furniture, which just allows you to, whenever you encounter a new situation, to immediately know where to fit all the pieces. It prevents you from saying the same thing over and over again, because now you just have new language that you can use. Right, I mean, even if you're not very sold on category theory in general, it's just a very good idea to have names for things that come up over and over again, instead of saying paper. If every single time you have to say, oh, can you give me one of those very flat things we used to write on? It just becomes annoying after a while. It's a lot easier if you just have a name for it. But then but then at some point in category theory, you really then at some second stage, you arrive at actual theorems inside of category theory, such as the adjunct. Oh, what just happened? All right, I don't know why that disappeared. But at some point, you arrive at actual theorems in category theory, such as the adjoint functor theorem. And but also a bunch of at some point you also arrive at constructions which are in some sense just like too hard to express one piece at a time. And this becomes especially important once you move into higher category theory or infinity category theory. There's like a lot of constructions where you can just no longer say, oh, it's the thing you get if you take this little piece and this little piece and this little piece, and then you stick them together in this way. Like you have to give the construction in one fell swoop for it to make sense. So let me just call this new constructions. So we get more questions. All right. So there are no more questions as far as I can tell. So let me just continue on my journey here. So at the current rate, I expect to basically arrive at the definition of I'll definitely be able to make it all the way to natural transformations, and then we'll see how far we'll get. Yes, exactly. So LinkedIn user asks, can we say that category theory is a language that abstracts mathematical constructions? This is exactly right. So so many of these things that form categories that we saw in the beginning here, like vector spaces, they are themselves already abstractions of something, right? So a vector space is itself ordinary abstraction of some situation where you have things that you can add and things that you can scale. So most people, when they think of vector spaces, they think of like lists of numbers basically that you can add and scale. But you can also add and scale continuous functions. Like you can add and scale frequencies or something when you're creating a signal. And because you're doing this thing over and over and over again, you give a name to it. You give it the name of vector space. So, and category theory then abstracts how these abstracted things talk to each other. So the category theory is an abstraction of abstractions. All right. So let's see. So I was going to define a monoid should have one more definition, one more thing to play with. So a monoid consists a monoid M. It is a triple so let's see, what do we want to call our composition? Let's call it star. Where M is a set, star is a map, going from M cross M to M, and E is an element in M. So this here is the structure. And the properties that these things satisfy is, so let me just number these and give the letters to the others. So this is 1, 2, 3, and the properties are A, associativity, namely that, so this here is denoted, so if you have two elements in M, then the composition is denoted N star M. With associativity, so we have L times M times M is the same thing as L times M times M. And then the identity axiom, which just tells us that, so this here is for all triples LMN. And then the identity, namely that for all M in M, we have that E star M is equals to M composed with E. And now here's a little exercise for you. A category is a category C such that it has only one object. So let's call this object 1. Is the same as a monoid. Right, so the way you should think of this is then that so the way to think about this is that the morphisms from C to C, from 1 to 1, are just going to be this monoid, which you can then compose. and so on. And then I don't know what the difference is between a set and an ordinary set. All right, so, and then for, if we have two monoids, M and N, a map, a monoid homomorphism F going from M to N is A mapped. So this is, we have this, a structure, we have a map. So observe that I just wrote the same thing twice. So here I'm secretly thinking of this here as a triple M star lower M E lower M, and this here as N star lower N E lower N, and as F as an abstract morphism. And here I really mean M, the underlying set. Right, so M the underlying set, and N the underlying set, and F and a bona fide map between the underlying sets, such that for all pairs M1, M2, and M, we have that M1 composed with M2, and we apply F to it, we get the same thing as F M1 star and F M2. And also that F applied to EM is equals to EN. All right. So Michael asked the correct question here, what do you mean by same as? And this is part of the exercise to really figure out what is meant here. But basically you need to figure out some way of making precise that from any monoid you can extract a category with only one object, and whenever you have a category with only one object you can extract a monoid. And so we can go from monoids to categories with only one object, and from categories with only one object to monoids. And you want to show that these two processes are inverse to each other. So if I go like this and then back again, I just get the same monoid that I started off with. And if I go from categories with one object to monoids and back, then I end up with the same category with only one object that I ended up with, or that I started off with, sorry. Right. So so before I tell you what a function is, let me just give you one more list of examples of categories. So, so where was I going with this? Oh yeah. So here's another example. Let X be a set. Then we can construct a category. Then we can construct a category. Let's call this, I don't know. And it's going to be very unimaginative and call it X underline with the object of X underline just being X, and then for all XY in X cross X, we have X underline Y is equals to id X if X equals Y, and oh sorry, this here should be the singleton, and the empty set if X is different than Y. Right, so in pictures, so let's say that X is the set consisting of A, B, and C, then X underline is basically A with an identity morphism id A going to A, and B together with an identity morphism going to B, and C together with an identity morphism like this. And again, I'm not going to write it down, but you could sort of do a similar exercise where you try to say that a set is the same as a category where where the only morphisms are the identity morphisms. Yeah, I'm sorry to see you go, Sebastian. Okay, so George would like to have a counterexample. So I think right. So I think George is asking whether any semi-group gives you a category in the way that I just explained, and I think that George has already understood what goes wrong, which is that if you don't have associativity, then you don't get a category. I don't think that a monoid. So LinkedIn user asks whether a monoid in set theory is an action on sets. This is not quite right. So you can have a set together with the action of a monoid on it, and then in general category theory, you can indeed define monoid objects in any monoidal category. Oh, right. So okay. So here's maybe a point of confusion. So the collection of all semi-groups and homomorphisms between them definitely form a category, but you cannot extract a single category from a semi-group the way I did for a monoid. Okay, so the where was I going with? Oh yes, right. I was going to give you the definition of a functor. So just as sets and set sets and maps and vector spaces and linear maps and topological spaces and continuous maps and so on, they all form categories. There is a notion of structure preserving morphism between categories themselves called a functor. And then categories and functors form a category. And so soon it will make sense to you why I introduced these two examples of categories further up. So flow just quickly define what a functor is. So we have definition. So if C and D are categories, then a functor, capital F, from C to D. Again, it has a bunch of structure. It consists of a map of sets from the objects in C to the objects in D. And then for all x, oops, that's not what I wanted to write. For all x and y, in C cross C, we want to have a map F1 from C x to y to D F0 x to y. And these satisfy a bunch of properties, namely that for all x in C, we have that F1 of id x is id y, and for all x, y in, oh, I was being a bit sloppy here. So this is the sort of sloppiness that you'll see that you'll see quite a lot. For all pairs, oh, sorry, for all triples even. We have that, and then for all maps, we have that F1 of F composed with G is the same thing as F1 applied to F composed with F1 composed with G. Right. So this function, so this definition was a bit less painful than the last one. And in general, people don't write these lower 0 and lower 1. I just put them there for clarity. So normally we'll just have F, 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 and so on. And now we see that in the case we already have two very simple examples. If x and y are sets, if x and y are sets, then a functor from x underline to y underline is the same as, in this slightly informal sense, as I meant before, as maps from X to Y. And our second example is that if M and N are monoids, then let's give it a name. Let's give a name to this construction here. So let's say that the category associated to a monoid is going to be, let's call it Bm. Then a functor from Bm to Bn is the same as a homomorphism from M to N. So this is nice. This tells us that this gives us some sort of consistency check. So every set can be viewed as a category, and any monoid can be viewed as a category. And if you view sets as categories, then functors between the associated categories are just the same thing as maps between sets. And if you view monoids as categories, then functors between the categories constructed from these monoids are just the same thing as monoid homomorphisms. Oh, did I make a mistake above? Oh, yes. Thank you, Michael. So this here should be id f0 x. Very good. Okay. So let me just very quickly give the definition of a natural transformation, and after that, I think there'll be time for me to go to bed. So definition given categories, so given categories C and D and functors F and G, then a natural transformation it's usually called eta, from F to G. So you can then write it like this. Is again, we have a bunch of structure for all objects X in C. You get some a morphism in a morphism do X going from Fx to Gx, and then we have some properties, or rather we have one property, namely that for all morphisms in C, the following square commutes. So we have right. So this x here gives us part of a natural transformation, but this y here also gives us part of a natural transformation. Fy to gy. But then the fact that f is a functor gives us a morphism like this, and that we can call f applied to f, and the fact that g is a functor gives us a morphism like this, which gives us g applied to f. And now we want this diagram to commute. So what does commuting mean? Right, commuting then means that going like this is the same thing as going like this. Or more precisely, first applying eta x followed by g applied to f is the same thing as first doing f applied to f followed by eta y. And okay, so let's see. So LinkedIn user has a question. So I like where this question is going. So let's see. So we started off with categories, and we get morphisms between categories, and then we get morphisms between morphisms and categories. So then the next natural step is to define morphisms between morphisms of categories. And for just plain old categories, there's no such notion. But there's a thing called an n category, and between an n category, you do get exactly this sort of thing. You get morphisms between n categories, and then get morphisms between n categories, and you can do this n+1 times. So let me just finish with a picture illustrating what's going on here, and then I think I'll be done for today. So again, so first we start off with an important observation. For categories C and D, we have that the functors from C to D, together with natural transformations, form a category. So this is again, this is a really good exercise to figure out, and we denote this category like this. So the C and D between square brackets. Okay. So if you know, so the following is only really useful if you know about currying. So what does currying tell us? Currying tells us that for sets x, y, and z, the set of maps from x cross y to z is canonically bijective to the set of maps from X to the set of maps from Y to Z. So in other words, if you have a map like this, you then send it to the map which sets X to the map which just has X plugged in the first slot and leaves the second slot open. And you can play a similar game with categories. So there is a category called I. So I is a category. And there's two objects called 0 and 1, and it has just one morphism between them. And you're able to, and just as for sets and groups and vector space and topological space and so on, you can take the product of two categories. And what you'll see is that and what you'll find is that you get you can apply currying to categories. So now if C and D are cats, you can consider the following equivalences of categories. So I haven't told you what an equivalence of categories is yet, but this here is mostly for intuition. Oops. So what this here is telling you is that for any category, a map from I to C is the same as just a morphism in C. So whenever you have some morphism in C, you can construct. So whenever you have the morphism F going from X to Y, then there exists a unique functor from I to C, taking 0 to X and 1 to Y, and this unique arrow to this arrow. And conversely, if you have a functor like this, then you can obtain X from looking where you send 0 and obtain Y where you send 1. And this here is a bit analogous to if you have some space, if you have X, some space, like a topological space or something, then a map from the unit interval into the space is like some sort of path. And if you know a little bit about homotopy theory, then you'll now see that this here looks very similar to a map 0, 1 cross X to Y for X and Y spaces. But over here, by what I just told you, any functor in here is the same thing as a natural transformation, right? Because this here is a category of functors of natural transformation. Any functor from Y into this category precisely picks out a natural transformation. So we see that a natural transformation can be viewed as some sort of directed homotopy between functors. All right. So the last part was maybe a bit confusing, but if you do know about these notions of continuous maps and homotopies between them, I think this is a really nice picture to have in mind, because now now you can really think of a natural transformation as some sort of deformation of one functor into another, a potentially irreversible deformation. Yes, exactly. So I is a category of precisely two objects and one unique morphism from the first object to the other. And just for completeness, let's also just note that both of these morphisms also have an identity. But I didn't want to clutter the picture. So now I've drawn all morphisms in here. So if I compose this identity, if I compose this identity here with the unique morphism, I just get the unique morphism back. If I compose this unique morphism with this identity, I just get the unique morphism back. All right. So if there are no more pressing questions, I think I will stop here. Thank you very much for your attention. Okay, Bombardier is back.
Yes, well done. Thank you so much. This was, I'm sure, the audience, very engaging, very, very interesting, and yeah. And I think now people have the baseline, the newbies at least. So we had two audiences here, like the basic people who didn't know who knew something about category, and those who didn't know anything. For the latter, hopefully you have something here that we don't have to repeat in the next coming session, so you can go and think about this, and maybe in the next session come up with more questions.
Right, so next time I'll talk about universal properties and adjunctions. I know that this is something that people are interested in, and then we'll go from there.
Yeah.
All
okay,
right.
So thank you to Adrian for this amazing session, and yeah, we see you next time. And don't forget, I'll follow up with everybody about the next session with the links and everything. So yeah, by the way, if you already registered for this session, you don't need to sign up again. Unless you want to ask a question, then we ask you to be on stage to get in touch, and then we can arrange that. But yeah, in the meantime, Adrian, thank you so much again for taking your time to do this. I will just end the streaming. Yep. Okay, so I'll see you next time. I'll just end.
Yeah, absolutely.